I'd like to make them believe is that a heart transplantation in humans can be accepted as palliative surgery.
Well, I think the time is right for the heart transplants. I think the basis for adequate immunosuppressive therapy has been laid. I think the technique has been established in the dog, and I think it's time it was done.
I don't want to even ask them to believe that we will prolong his life, although I think we do prolong his life, but they don't even have to believe that, as long as they believe that we do palliate.
I think also that one can say this because it has succeeded. Nothing succeeds like success.
We've been waiting for you, so...
I haven't been, it was not within my control to get there in time. Unfortunately, there was some trouble with the plane in Amsterdam, and then we got headwinds again.
Right.
Look out, boy, you think to fall over that.
Spring, 1968. World leaders in organ transplantation are gathering in Boston, Massachusetts to discuss their work at the first annual John F. Kennedy Symposium. This is the story of that meeting. The Transplanters' story.
Have you been to Boston before? Any particular emotion or reaction coming here for the first time?
Well, it's supposed to be, the beginning and the end of medicine,
Well, you have many of your friends here. I know Dr. Merlin Dicker is looking forward to meeting with you. There's many parallelism in terms of the kidney transplant.
Sure, yeah.
Did that influence you in terms of your work at all? The
Kidney transplant?
kidney transplant.
Oh yes, I mean all our knowledge of how to go about detecting rejection in the heart is from our experience with kidney transplant.
And do you find them basically similar?
Just the same.
Just the same.
Just the same.
We got started because of the artificial kidney, which, George Thorne established there. When we found we could keep people with hopeless kidney disease alive, the next step came give them a kidney which would keep them alive on their own. And this, of course, enabled us to do that.
What was your emotional involvement at that time, the first time here was indeed an organ transplantation?
Well, I think we were all so excited that I don't really think that any of us worried too much about it. There was too much new, too much to be done. We were all so busy. But the thing we did worry about was the first identical twin transplant, because we had reason to believe that this was going to work. And also, it was the first time that anyone had taken a healthy, normal kidney from a living donor. And in addition to all this, it was done on the 23rd of December. You can imagine in the present climate of heart transplants and all, what would have happened if that first normal, healthy donor had died on Christmas Day. The whole transplant business would have been down the drain for years, certainly.
I don't know whether you ever read that story about my mother and the plum tree.
No, I didn't.
No, you didn't?
No.
Well, we had a plum tree in our garden, and sometimes it was very full of fruit, and then branches would hang way down on the ground, you see. And my mother, when we had success at school and we were sort of full of ourselves about this, my mother always said, look, you must always look at that plum tree. When it's really full of fruit, its branches are low onto the ground, you see, and that's what you must do. When you really have success, then you must be down on the ground, not up in the air. And that's the style of advice that I've tried to follow. It's just about the first time at least in the history of my country, and I think in the history of other countries, where young people have been interested in a scientist and not in a sportsman, or in the past their heroes have been boxers or baseball players or in our country rugby players, and not really scientists not been there, sort of the man that they've been enthusiastic about. And I once had the opportunity to speak to some students in Italy and ask them, now tell me why are you so excited about it? They said, well, the reason is that in you we see a young man that's achieved something. And therefore we feel there's hope for us. But I think there's a little more to this, that I'm not so young, but I appear young, you see. But anyhow, they see a young man who's achieved something, and they want to see what he looks like. And then what they see is that he's just the same as they are. There's nothing fancy about it. You want to become a boxer, you see, and you say, well, I'm going to have a look at the boxer now. And there you come and you see a man with enormous muscles, you know, a really well-built man, and you realize, look, I can never become a boxer, because that's the type of man who becomes a boxer. You see a man who's done heart surgery, transplant heart, and you see him, he's just an ordinary man. So the youngsters now feel, look, there's hope for us. There's nothing that he's got. He's got no qualities that we don't have. And therefore we can also achieve something one day in the world.
I'm very, very grateful for being invited to this city. It's the first time that I've visited Boston for medical reasons, and you may say that's been a real shortcoming in my education, because they say you can always how does it go about this Harvard man? Oh yes, you can always tell a Harvard man, but you can't tell him very much. Can I have the first slide, please? They always ask me, Dr. Barnard, why did you do the first heart transplant in Africa? I'd like to just point out to you that this is Africa, and that is where the first heart transplant was done. That's Cape Town, South Africa.
And how long did the operation take?
I don't know how long the operation took. I've got no clue when I even started. I don't know how long. You can ask Dr. Zinski in the institute, because he's got the time.
And what's the patient's condition now?
Very well.
The unlikely idea that old organs could be replaced with new ones and withered limbs with strong ones is as old as the history of man. As early as the 13th century, it was believed that Saints Cosmas and Damian miraculously replaced the gangrenous limb of a dying man with one from a dead Ethiopian slave. At least, so goes the legendary tale. Ill-conceived attempts at transplantation then grew out of the scientific flamboyance of the Renaissance. But it was only in the 19th century, with the fledgling work of Baronio and Bünger and the brilliant Paul Bert, that scientific order began to grace transplant research. Then, in the dawn of the 20th century, the first of the transplant visionaries, Nobel laureate Dr. Alexis Carrel. Carrel perfected the delicate blood vessel surgery which enabled limbs and organs to be transplanted in animals. Yet, despite successful surgery, each of Carrel's organ grafts mysteriously stopped functioning. Bewildered, but acting on an intuitive hunch, he wisely suspected that his surgical prowess was unveiling a previously unknown biological force. Almost a half-century later, Sir Macfarlane Burnet would begin to define Carrel's mysterious force in terms of the clonal selection theory of immunity. During embryonic development, Burnet theorized, those specific clones, or colonies of immune cells, capable of reacting to the embryo's own tissues, are somehow suppressed or killed. By the time of birth, the body therefore recognizes its self-antigens and tolerates them, but rejects foreign antigens, such as bacteria or viruses or transplanted organs from genetically dissimilar donors. The visionary torch, sparked by Burnet, now passed over to Sir Peter Medawar in England. The British group, working in the 1940s and 50s, designed a series of meticulous experiments that brilliantly supported the theories of Burnet and ultimately laid the foundation for all future transplantation research. Soon, the giant step from the laboratory to the patient's bedside was made with this first artificial kidney, and by an improbable team of physicians. The famed Hersey Professor of Medicine at Harvard, Dr. George Thorne. Willem Kolff, the Dutch physician who developed the first artificial kidney during the Nazi occupation of the Netherlands. And researchers John Merrill and David Hume of Boston's Peter Bent Brigham Hospital. On December 23, 1954, after treating a terminally ill uremic patient with Kolff's artificial kidney, this team presented their patient with an unusual Christmas gift. A transplanted kidney from his twin brother. A kidney that spanned the gap between Karel and Cape Town.
Well, this is what's happened today. Sic transit gloria. This is the first artificial kidney that was ever run in the United States. Here it's ended up in the junk pile. This is the thing that started it. This was the one that Dr. Carl Walter designed, and I helped perfect with Dr. Thorne's help after the original design of Dr. Willem Kolff in Holland. This old apparatus used to work by winding cellophane, which actually was sausage casing on this drum. We had to sterilize this sausage casing ourselves by boiling it. We then wrapped it on the drum, and the blood went into the sausage casing through this hole here. And then the motion of the drum propelled the blood from this end down to here. And in so doing, it passed through a salt solution, which was in the bath here, and the poisons came out of the blood in the cellophane into the bath, and then we could remove them by changing the bath. Here the old instrument panel with the heater, the lights, the pump which propelled the blood down, and this was even an old gear shift here so that we could put it in neutral if we needed to while we changed the cellophane and occasionally repaired a leak or two. This was the apparatus that enabled us to maintain patients in good health, patients with chronic kidney failure, until we could get transplants for them. I think it's a reasonable thing to say that without this thing, transplantation never would have gotten started, because in the early days, before we knew much about it, we couldn't take live donors. We had to use cadaver donors. And therefore, of course, we had to keep the patients in good shape with this old rotating barrel until a cadaver came along.
I'll never forget when we hitched up the first kidney, and we hadn't expected it to put out urine immediately because the previous ones had not. The previous ones put out urine only after several days. This one worked immediately on the table and poured out copious amounts of urine, and of course we were delighted. But I never dreamed that transplantation would be this far along 15 years later. It's been quite surprising.
Dr. Murray, how many transplants, human transplants, have you personally been involved with?
Well, we've done close to 200 here at the Brigham, and I've been in charge of the surgical side of the program since 1954.
And during this period, what has been a major disappointment for you? Have there been some?
Oh, yes. I can recall several patients now dead that could be alive or would be alive had we known as much at the time that we transplanted them as we do now. Some died early from overdose of drugs when we didn't really have enough knowledge of the proper dosage. Others died with perfectly normal kidney function of secondary infection that we might have been able to anticipate had we been a little bit wiser.
Had we been a little bit wiser, a familiar phrase in the history of medicine. But important advances have been made since those early days, and now a patient receiving a related donor kidney transplant has a 75% chance, or better, of long-term graft survival. To many, this alone would be a great achievement. But it is not good enough, say the transplanters. And to make the chances better, the secrets of immune rejection need to be unlocked. Rejection seems closely related to the function of a family of cells called the small lymphocytes. These lymphocytic cells somehow become activated by foreign tissues and respond by causing the body's immune system to produce the antibodies and scavenger round cells that ultimately lead to graft destruction. To transplant researchers, the mandate is clear. Suppress rejection while preserving the body's ability to ward off infection. Harvard's Dr. Richard Wilson wrestles with that problem.
Well, I think that basically the problem in transplantation is still one of the immunologic rejection mechanisms. And more patients die from overdoses of drugs than anything else. Therefore, better biologic adjuncts must be the most important of these aspects.
What research is being done now with immunosuppressive drugs in terms of the research lab itself?
Well, there are a few new drugs that are being studied, and some old ones as well. But basically, until we find a perfect drug, the biologic adjuncts are going to be more important, because we have a drug program with Imuran and prednisone, which isn't bad, but most patients need additional help. And this is where things such as anti-lymphocyte serum and desensitization or pretreatment with specific antigen may be the important answers.
Biological immunosuppressives. Until very recently, this term did not even exist in medicine. Chemical suppression of the body's immune system carries with it side effects which make long-term use difficult, even potentially dangerous. For this reason, anti-lymphocytic globulin, called ALG, offers great future promise. ALG is obtained from the serum of animals inoculated with human lymphocytes. When administered to transplant recipients, it somehow inhibits the body's lymphocytes and thereby markedly blunts the graft rejection process. Transplant researchers now work to discover the secrets of biological immunosuppressives.
The lymphocyte is particularly sensitive itself to the action of serum antibody, so that it seems relatively simple to think that one could make an antibody to lymphocytes, which administered to a recipient animal would destroy or incapacitate his lymphocytes and therefore blunt the effector mechanism.
Theoretically, there is a very good basis for using biological immunosuppressants, a basis which may assist the host in maintaining a graft without weakening his defenses totally to infection. In the doses we've used of anti-lymphocyte globulin, we find the lymphocytes disappearing from the bloodstream. This is a very simple explanation that we're just knocking the lymphocytes out. However, other investigators with other dosages, with other products, perhaps to spleen or to lymph node rather than to thymus, which we use, find the lymphocytes are increased, and they think that they're being stimulated to sterile replication so that they're not capable of acting on the graft. They're just wasting all their energy reproducing themselves.
When we set out on our program for heart transplant, we wanted to use ALG, believing that it was the best thing. Of course, we use Imuran or azathioprine, and we use prednisone and hydrocortisone and these other drugs, but we have a great deal of confidence in the ALG at this time.
Immunosuppression is necessary because donor tissue is genetically different from recipient tissue. To learn how these differences might be typed prior to organ transplantation, Dr. Ronald Guffman of the Peter Bent Brigham Hospital studies the genetic characteristics of inbred rat strains.
Now we know that if the genetic barrier between donor and recipient is great, we find that the kidney survival is very short. However, in this group of animals, we've minimized this barrier by matching the strains of rats used, and we find that in this group of untreated animals with only their transplanted kidney in place, we have survivals that are longer than 4 months. Therefore, this tells us that for the future of tissue typing, we must define the antigens on that are determined by the strong locus in man, and that hopefully with matching at between donor and recipient of these antigens, just as we can type for the antigens on the red blood cell, that we can expect to be able to graft kidneys, use minimal immunosuppression, and have a good clinical result.
surgery, immunosuppression, tissue typing. All have helped the otherwise doomed. Kidney transplant patient John Riteris has returned to his work as a college professor.
John, how long ago was it that you had your transplant?
9 years now, a little over actually.
9 years. The fact that you've gone this well and done so well, I think is very exciting.
It's certainly exciting to me.
Louis Fierro, a heart transplant patient, returned to the living.
Dr. Coley is the man with the golden hand, the only man with the golden hand.
He gave my husband life.
They said, don't you feel bad that a patient's got to die before you can do a heart transplant? I said, well, tell me, did you ask the other surgeons whether they feel bad because a patient's got to die before they can do a liver transplant because they've just done a liver transplant also in the same period? I said, no. I said, what's the difference? I mean, you never query the death of the donor when you deal with other organs such as the liver and the kidney, but you always query the death of the donor when you deal with a heart transplant. And there's really no difference between the two. Well, they said, it's all this emotion and the mystique about the heart. But I mean, I don't think that our scientific thoughts and judgments should be clouded by mystique and all that.
Yes, I think you're quite right. I like to phrase it this way. I think that there is a lot of emotion attached to the heart, to motherhood. And I said the reason perhaps that it isn't, people don't get excited about the kidney is because you never see a kidney on a Valentine card.
Yeah. It's interesting that if you go into in the Bible, the heart is mentioned, I think, 800 times in the Bible. The kidney around about, I think, 27 times. And the lung is never mentioned once in the Bible. Yeah. But I mean, from 800, the next organ is about in the 20s, so it's 30. It shows you what an important organ has been throughout the age.
Well, let me ask you a question now. I sit on a number of committees having to do with ethics and morals, and we're terribly concerned about the death of the donor. How do you approach this? When is a donor dead so that you can take their heart?
When is the donor dead so that you can take the kidney out?
No, heart.
When is the donor dead so that you can take the kidney out?
Well, we think the donor is dead when they have fixed dilated pupils, have no reflexes, they need assisted respiration, and they have a flat electroencephalogram for at least 24 hours.
Electrocardiogram?
Electroencephalogram.
What about electrocardiogram?
Well, the electrocardiogram, you can keep going artificially.
Well, we go further. We have all those criteria in addition to flat electrocardiogram.
Really?
Yeah. So there's really no difference between the donor that's used for kidney transplant or for liver transplant
I'm sure.
and the donor that's used for heart transplant. In fact, the heart, as you know, is an organ that tolerates anoxia extremely well. It may even tolerate anoxia better than the kidney.
I think it does. And most of the people I've talked to, theologians, social scientists, philosophers, and so on, feel that the decision, as I think you feel, is in the hands of a well-motivated surgeon who is guided by his peers.
Like they asked me, they said, well, when is the patient dead? And I said, patient is dead when the doctor says he's dead.
That's right.
Yes, Dr. Kubeki.
How are you? Nice to see you.
Say, well, what's your series now down here?
Yeah, I heard.
When Lincoln sent me that cable, he sent me a cable. He sent me a cable when I did my first heart transplant. Congratulations, I'll be reporting on my own series soon. I thought he was joking, but he wasn't joking. He really came to do it.
I've been away, I haven't been on the road ever since this all happened. I don't know anything about the cases.
Have you had breakfast, Dr.
Yes, thank you. Thank you.
Well, we were talking a lot of jazz here. Well, they often ask me whether during this period I've had some moments that really meant a lot to me. I think there are two periods that sort of stand out in my mind. The first was, of course, when you saw a patient with a pericardial cavity with no heart inside it, which I don't think anybody has seen it except on the post-mortem table. And the second one, which I thought was even more traumatic, is when like 3 weeks after the heart transplant, the second patient, he asked me to have a look at his heart that I studied removed. And we had it all nice in a bottle. and I took this heart to him, and I realized that this is the first time in the history of man that a man was able to look at a heart that has kept him alive for 58 years. And he's a dentist, so he has a little medical knowledge, so he looked at it, and I showed him the scarring and the occluded carnivores, and he said to me, he said, I'm glad I don't have that heart anymore.
Well, he agreed with your diagnosis.
Yeah.
Take you to get educated after college?
After college, a long time, about 20 years. No, wait a minute, now, 10 years after college. That doesn't include medical school. If you include medical school, it's 16 years.
Good grief, that's more than I've lived on this earth.
That's right. So you see, it takes a long time to do these. But you mustn't give up. Just keep going. Okay.
Adulation is not lacking at this symposium. But neither is scientific disagreement lacking. Honest disagreement.
The mechanical devices hold great promise because they can be manufactured on a mass scale, can be precisely tailored ahead of time. There can be many sizes. And I do think that these should be developed together.
There's no doubt about it that the heart is a perfect organ, and as much effort as our scientists put into the problem of trying to create an artificial heart, it's a compact energy source, and we can't build an artificial heart so compact. It's amazing. The Lord did a very good job.
Rejection, as you know, is a problem with heart transplant, and it would be very useful if one had a mechanical device which could hold the patient over a rejection crisis.
By the time you're sick enough to need a transplant or many other things, you're pretty far gone. And we've got to work to prevent the diseases for which transplants are needed. So I'm much more in favor of emphasizing prevention rather than such extreme measures of treatment. You've got to have them. I have no objection. They're dramatic. But they're not the last word by any means.
But I think what one must always strive for is the perfection of the prosthesis to a degree in which you don't have to consider these other problems. Work in parallel, and we've done that from the very beginning. We developed homographs, prostheses, parallel. And as one came towards the head, that became the method of choice. The other moved, then we moved into it. There was a time when Mike Leakey told me that he was never going to stop using homographs in arteries because there was no possibility that I could develop a prosthesis that would be as satisfactory as a homograph. And that's in the SGNL.
Yeah. Naturally, one can only speculate about mechanical hearts at the present time because we do not have a true mechanical heart. But it's conceivable that with further research and development, it becomes possible to develop the mechanism in such a way that we can overcome certain problems that exist today, such as the blood interface problem, the control mechanism problem, and the energy source problem. Why it could be developed in such a way that the potential, let's say, stroke volume and output of such a mechanical heart can be controlled. Because if, for example, we had at this moment an artificial device comparable to the artificial kidney in relation to kidney transplantation, the whole procedure of cardiac transplantation would be more widely accepted and more
traumatic.
Yes, and also, well, not only traumatic, but in the sense that it would be a more readily available clinical method.
You know, that's why it always worries me now on a program that you see mechanical heart versus heart transplants, because at this stage, with our development at this stage, they both have a place in the treatment of disease.
As you well know, there's a school of thought whose argument runs something like this. The heart is nothing but a pump. We have tremendous electronic engineers. We're going to have atomic power and so on. Therefore, why not concentrate upon making an implantable artificial pump? It isn't like the kidney, which is so complex metabolically, it's really a pump. And therefore, one should be able to design a pump and make it work.
Well, I agree with that. What I say to that is, you may have heard the story of the Texan and the man from Fort Knox who were arguing about the wealth of their various states. So eventually the chap from Fort Knox, he got fed up with the Texan. He says, listen, he says, we've got enough gold to build a solid wall of gold around Texas. So the Texan said, you build it and we'll buy it. Well, the same with the mechanical heart, you know? You build it and I'll buy it.
The new school of cardiac surgeons, mentored by surgical greats like Wangenstein and Lillehei, all strike a central chord. They are leaders,
well, it's
innovators.
That's a long story. You know, we started about 10 years ago here, actually at the time this medical center opened. And we got interested in it because we were doing procedures on animals where we were able to stop the heart for longer and longer periods of time. So the idea finally developed that maybe we could stop it long enough to actually replace it, taking the heart out of one animal and putting in one from an animal of the same species. And so this actually happened, and we were interested at the same time, too, in correcting some congenital defects in children by removing the heart and then operating on it, for example, at the back table and then replacing it. So with this idea in mind, we developed a technique or a method, a simple method, for replacing the heart. And of course, after we'd done this a few times in the same animal, we were able to do it by removing the heart, discarding it completely, and then transplanting one.
In transplanting the heart, we had a very brief delay from removing the donor heart and having it hooked up to the circulation of the recipient. The average time was somewhere less than 45 minutes in each of these. We kept the patient's temperature normal, and we kept the donor heart as normal to normal temperature as possible. We took particular precautions to preserve the conduction mechanism in the donor heart. And this, of course, is extremely important. And some of those that have been reported, they have ignored the sino-auricular pathways for the conduction system, and this has put an added handicap on those patients. And I think it has accounted for some of the early demise of some of the patients.
Now then what we did is then we opened the back then of the right atrium by cutting from inferior vena cava to superior vena cava, leaving us now an area like this, leaving us an area like this now when it's open that we could anastomose to. An area like that we could anastomose to the part of the right atrium that we left in the patient. Then what we did is we cut away the back of the left atrium, leaving us an area like this, which we could anastomose to the part of the left atrium that we left in the patient. So this is the suture line would run along this area here and would run along this area here. Now you can see with the suture line, we're not near the septum. We never stitch near the septum. Here the suture line runs and here the suture line, and we don't stitch in the septum at all.
I think that to do a thing like this, you need a lot of research work, which we've done. You need a hospital where you can do big open heart operations, which we've done for the last 10 years. You need the nursing staff that can look after patients before, during, and after operation, which we have. You need a man like Duval who's got the courage, or whatever it is, that a man like that needs at a time to give his daughter's heart, just after his wife has already been killed. We have a man like Wisconsin that was keen to get better and who was willing to risk or to have confidence in us to do something for him. And then I think the final thing, you must have faith in yourself and faith in your God. And I don't think there's any problem in doing things like this.
We must regard heart surgery as something less than a proven therapy. It's experimental at this point. You should have the tragic, cold, cruel feeling of being called in the middle of the night by somebody whose closest of kin is dying of heart disease, asking you to do an emergency transplant. I can't do it. It isn't that kind of treatment. Or conversely, be called by a fellow physician who says, my wife and I have our most precious possession, our 19-year-old son, decerebrated after his motorcycle accident. Do you want his heart? They're serious, sober people. Yet I cannot with conscience tell them that I can use that heart, nor can I salvage that person who's dying for want of a heart. We aren't in that phase of the art of the science. But I've always had contempt for the doubters. The guy who always says, I don't think it'll work. You know, he has a great advantage over the fellow who's trying something. The guy who says, I don't think it'll work, has much more chances of being right than the guy who tries something positive. So it's those delicious victories of the doers over the doubters that I'd like to emphasize. As a matter of fact, in 1896, one of the greatest surgeons in the world said, the heart alone of all viscera has reached the limit set by nature towards surgery. No new method and no new technique will overcome the natural obstacles surrounding a wound of the heart. That was Sir Stephen Paget, the greatest surgeon living. And yet that year, Reign of Frankfurt successfully sutured a stab wound of the heart, made a fool of it. And this is as it should be. It was one of those delicious victories of the doers over the doubters. Now, I don't want to be a doubter here. I want to be helpful to the doers, but I think it has not been totally satisfactory as an experiment so far.
I would agree that this is an experimental procedure, but I believe the use of penicillin at one time was an experimental procedure, and that this is a definite, realistic possibility, which I think it is to the everlasting credit of Dr. Barnard and Dr. Shumway and the others who have done this procedure, that this must be explored.
Now I find that you can have each of you 45 seconds, which would be more than a sentence, to describe what you think will be going on in 1978 with respect to transplantation of the heart.
Well, if you're starting at this end, I assume the meeting will be on June the 6th, 1978, your 92nd birthday, and that you will be here chairing the panel, and that we will discuss the relative merits of tissue transplants versus totally implantable self-energized units, and it'll be a standoff.
Do you think we can invent any more transplants of other organs that we don't have yet? Will we be here? Have I heard that in Cape Town, Dr. Barnard, there's a sign on that famous driveway where I was supposed to be riding a bicycle once, which says, drive carefully, Dr. Barnard is watching.
That's correct. I think it's very difficult to look into the future, but one thing I can predict that in 10 years' time, Dr. Harkin will be doing our transplant.
I think you've met us now. We're ordinary guys. There's nothing about us. It's superlative, and we know heroes. I think that what made this the people, the first heart transplant, was just that we are doctors and we try to save a human being's life, and I don't think there's anything special about it.
Some see things and say why. Others dream things that never were and say why not.